So now we're in section 2.4, and we're going to be looking at other values that are used to describe a data set. These are values that are going to measure the amount of variability we see in the data set. We'll be looking at the range, the variance and standard deviation of both populations and sample. We'll be learning how to use the empirical rule. We will be skipping over Chebyshev's theorem and sample standard deviation for group data. The range, we've seen the range before when we were looking at frequency distributions in section 2.1. The range is just the difference between the largest value and the smallest value in the data set. Data must be quantitative to find a range, and it's max minus min. So here we have a set of 10 starting salaries for the 10 graduates that this corporation has hired. Let's find the range of the starting salaries. Now what we're looking for here, so let's order the data because it's helpful to find the least and the greatest. So here's our greatest data entry, and here's the minimum. So 47 minus 37 is 10. So the range of the starting salaries is 10 or $10,000. The range is the simplest measure of variability to compute, but it is also the least informative because it only uses two values, the minimum value and the maximum value. Next, we're going to look at deviation. Deviation is the difference between a data value and the mean of that data set. First, we're going to look at the population data set, the population deviation, which is x minus mu, the population mean. So it's each value minus the population mean. Or we could find the sample deviation, which is x minus x bar. Remember that x bar is the sample mean. Going back to our example with these 10 graduates. Now, if we are only interested in these 10 graduates, and this is not a sample from a larger population, then the first thing we need to find is the population mean, mu. Add up these 10 numbers, divide by 10, and we get 41.5. So the average starting salary is $41.5 thousand. To find the deviation is easiest if you set up this table. So you put all the x's in a column, and then take each value minus the mean. 41 minus 41.5, 38 minus the 41.5, and you get the deviation from the mean for each value. When you sum the deviations from the mean, you will always get 0. The physical descriptor of the mean is the fulcrum on a seesaw in the playground. So that for balance means we have to have the same amount of weight below the mean as above the mean. In order to get by so that it does not sum to 0, what we're looking for when we're trying to end up getting the average deviation from the mean. And to get an average, you would add up the deviations and divide by 10, or the number of values we had. But you can't do, but if you divide 0, the deviation is going to be 0, and clearly these numbers are different. So the trick we're going to do is we're going to square each of those numbers. So when we take each of the deviations and we square it, then we add up the squares. So we are summing the squares. Divide by n, the size of the population, and we get what's known as the population variance. The problem with the population variance is we have also squared those units. And so we will have units squared. In our example before, we'll have square dollars, which does not mean anything to us. So if we take the square root of the variance, we get the population standard deviation. This symbol here is the lowercase s, so we call the population variance sigma squared. Sigma is is s in the Greek alphabet, and this is the lowercase s, and the population standard deviation is known as sigma. And now we have our units back to our original units. So to find the population variance, the very first thing we need to do is find the population mean. Then we find the deviation of each of the entries by setting up that table, square each of the deviations, add up the sum of those squares. Then to find the population variance, you divide by n, the size of the number in your population. To find the population standard deviation, you take the square root of the variance. Let's go back to our example and recall that the population mean was 41.5. And so here were the deviations we had. Now we have squared each of these deviations. We took this number and squared it, this number and squared it, and we get the squares. Now we're going to sum the squares and get 88.5. To find the population variance, we take 88.5 and divide by 10 because we had 10 numbers, and we get 8.9, but that's 8.9 square dollars, and we would really like to have our original units of dollars. So we take the square root of that value, and we get approximately 3. So the population standard deviation is about 3,000, or in other words, the average deviation from the mean is about $3,000. To do the sample, we do everything the same, except in the very end, instead of dividing by n, we divide by n minus 1. But again, we still have our units squared, so we take the square root of the variance and we get the standard deviation, which brings us back to the original units. To find the sample standard deviation, you find the mean, you find the deviations from the mean, you square each of the deviations, and you sum the squares of the deviations. All of this is, these first 4 steps are exactly the same whether you're finding sample or population standard deviation. Then to find the sample variance, you divide the sum of the squares by sample size minus 1. And then to find the sample standard deviation, you take the square root of the variance. Back to our example. Now notice this table is exactly the same table we had when we found the population standard deviation. But this time we take the 88.5, instead of dividing by 10, we divide by 10 minus 1, or 9, and we get 9.8. But this is again in square dollars, so we take the square root of that, and we get 3.1. So the sample standard deviation, or the average deviation from the mean, is about $3,100. Using technology, there's a lot of technology that can be used to find standard deviation. You can use statistical software like Minitab or SPSS or SAS. You can use some of the nicer calculators like the TI-83 or 84, or Excel. Since I did not require you to purchase any of this technology, we won't be using technology in this class, but I just want you to be aware that it is available to you. Let's interpret standard deviation. Now remember, standard deviation is a measure of the typical amount a value deviates from the mean of that data set. The more the entries are spread out, the greater the standard deviation. Here, all the values are the same. They're all 5, so the mean is 5 and the standard deviation is 0 because we have no deviation from the mean. Here, the average deviation from the mean is 1.2. The mean would be right here in the middle. Remember, the mean is still 5 because it's symmetric, so the mean is found in the middle of symmetric data. And the average deviation of all the values is 1.2. This one, notice, is more spread out, even though we have this gap in the middle, but it's more spread out, so it has a higher value for its standard deviation. We can interpret standard deviation to interpret what the data looks like. As long as we know the data is symmetric and bell-shaped, we know that about 68% of the data lies within plus or minus 1 standard deviation from the mean. About 95% lies within plus or minus 2 standard deviations of the mean, and about all of the data, 99.7% of the data, lies within plus or minus 3 standard deviations of the mean. These numbers, though, only hold as long as the data is symmetric and bell-shaped. So here's this data here. Looks like the bell shape is symmetric and bell-shaped. It's symmetric about the mean. So we expect about 68% to lie within plus or minus 1 standard deviation of the mean. This is the mean plus 1 standard deviation. Here is the mean minus 1 standard deviation. Because the data is symmetric, this 68% is split exactly in half by the mean. So 34% to the left of the mean, 34% greater or large, or to the right of the mean. 95% lies within 2 standard deviations, and again, 47.5% is smaller than the mean, and 47.5% is larger than the mean. And almost all, 99.7, lies within plus or minus 3 standard deviations of the mean. That other 0.3% is split evenly between these two tails. 0.15% down here in this tail and 0.15% down here in this tail. Let's look at an example on how we would use the empirical rule to describe the data set. So suppose the average height of a woman is 64.3 with a standard deviation of 2.62. This is a sample mean, so this was taken from a sample of women. Now the 64.3 is the mean, and so we're looking at trying to figure out how many standard deviations is 59.06 from this mean. So we take 64.3 and subtract 2.62, and then subtract it again, and we find that we were at 2 standard deviations below the mean. So the distance between the mean and 2 standard deviations below is half of this 95%, or 47.5% of the sample of women are between 59.06 and 64.3 inches, the mean of the data set. Chebyshev's rule does the same thing, except the data does not have to be symmetric and bell-shaped. We are not going to be doing any problems with Chebyshev. Just know that it exists. So we'll skip through these slides. And we're not going to be doing standard deviation for group data either, so we can skip through these slides also. That's the end of section 2.4. You should now be able to find the range of a data set. You should be able to find the variance and the standard deviation of both a population and a sample. And you should be able to use the empirical rule to interpret data using the standard deviation. It's now time to go to my math lab and do homework 2.4.